And now we'll transition to our panel discussion. Bertrand will stay right with us, where we'll hear from folks with experience. Yeah, you don't get off so easily, Bertrand. We'll hear from folks with experience in both ground-based and space-based instrument design and commissioning. I have a few questions for them, but this is also your chance to ask for their experience in developing instrumentation and related career advice. Oh yeah, let's make sure we're visible on the GoPro. So that folks online can see. All right. Yeah, sounds great. You guys should sit, because I think you'll be more visible than me. There we go. And I don't think we need to screen share. I think we won't be using these slides, but yeah, I think we'll maybe only use them if we have to. I know there were some backup slides, but maybe if we turn the screen share off, then the people online will be able to see everybody talking. Would that be better?
Can you check with Megan, make sure they can see? I think it should.
Okay.
I don't think it matters with the screen share.
So in any case, I wanted to start out very quickly by just passing the mic down the row, and rather than introducing people for them, I think in your own words, it would be nice to hear a little bit from each of you about where you are now, what your career path is, and what instruments you've worked on.
Sure. So I'm Michael Bottom. I'm a professor at the University of Hawaii, and for career path. Let's see, when I graduated college, I worked as a stock trader, and then I thought there was more to see than that. And I went to grad school afterwards here at Caltech. And then after that, I worked as an engineer at JPL on the Raman coronagraph, mainly on the wavefront sensing and detector side. And from there, I moved to the University of Hawaii as a faculty member. So I mentioned some of the instruments, Raman in particular. Also have worked on instruments at Palomar, Keck, and Subaru.
Thanks, Mike. You actually remind me that I had another career before going into astronomy as well. I was an engineer. I worked on oil platforms for 6 months, and then I was like, okay, there's no way I'm going to do that for the rest of my life. I'm glad, because then I went to Hawaii. Not as much as you. So then I went into astronomy for a year, allegedly, just to see if I liked it, and it was 30 years ago. I started with working on nulling interferometry for exoplanet detection, because that's the way we thought we would do this job of direct detection originally. And then, 10 years later, it was kind of decided that coronagraphy might be a better solution for this. And so I switched to coronagraphy. And then I worked on the Keck nuller, the TPF interferometer. Then I worked on the Raman coronagraph back in 2012, 2013, when we started to get a bigger telescope to work with it. And then I also worked on the HEBEC study, which some of you may have heard of, and now on HWO. So yeah, we are getting finally close to a real mission. Still 20 years away, but after 30 years of work, I feel like it's a success.
All right. My name is Dimitri. I'm a professor of astronomy here at Caltech, and I'm also a senior research scientist at JPL. I've been here for about 10 years, so if we are going back in time, talking about funny things that I almost did and didn't do. I wanted to become a cook, a surgeon. I considered the military for just 2 weeks, and I finally decided to go into engineering, and I did most of my undergrad and grad school at the University of Liège in Belgium. I also spent some time in Paris, at Paris Observatory and the IAS, and where I think Bertrand spent a lot of time as well. So I worked more than 20 years ago on developing technologies for the MIRI coronagraph, so the 4-current phase mask that led to the discovery yesterday. I spent a lot of time on that when I was a grad student. I worked on technology developments for nulling interferometry as well. And I came to the US after my PhD on coronagraphy, and I did a postdoc at JPL for a while, and then I went to Chile to work at ESO, and I participated in the commissioning of the Sphere instrument. And then I came back here in 2015 to create a new group, and many of which are in the room today. And we are working on developing coronagraph technologies, building instruments for Keck Observatory, the 30-meter telescope, and doing a lot of fun stuff, a lot of good science as well. So here it is.
Start out with a few questions of my own before we open up. Maybe it would be interesting to hear, both for the ground and for space, what are some of the major phases in instrument development, all the way from concept to execution, and what are the timescales and how do they differ between ground and space?
Do we want to start with the ground or space?
Ground, go ahead.
Okay. All right, so that depends really on the scale of the instrument you have in mind. So let's start with the small instruments or upgrades to instrument. So those typically go fast, obviously, because we're talking about incremental upgrades to an existing facility. So that's of the order of a few months for incubating the ID and then developing the concept, maybe up to a year, and then another year to implement it and test it on Sky. And I would say the cost for those ranges widely between a few tens of thousands of dollars to a few $100,000s. So in the medium scale, now I'm talking about facility class instrument for telescopes like the VLT or Palomar or the Keck telescope. We're talking about phases, conceptual design phases of a year or so at least, followed by a preliminary design of a year or two, and then the implementation phase, which can last also a few years, and then the commissioning phase at the observatory. And the cost, I think the median cost for an instrument on a ground-based telescope today is $10 million for a medium-scale instrument. Now that we are seeing more and more of these mega instruments on existing 8-meter class facilities, and obviously on the extremely large telescopes. And now you multiply all these numbers by 2 to 10, right? So we've heard about METIS this morning, that it took 15 years, or it would take 15 to 17 years. And the cost, if you add the hardware cost to the number of people working on a project, I learned this morning 700 FTEs means 700 people are working for a year. That's enormous, right? So we're talking about a total cost for these instruments of the order of $100 million.
Yeah, that's pretty crazy. So, believe it or not, we actually didn't know about some of the questions, so we did prepare a little bit. So yeah, that was some stuff that Dimitri prepared, if you want to say more, but we can also make that available. On the space side, same kind of things, right? I mean, there's pre-formulation, formulation work, and implementation work. Things cost a lot more, even more than that. So basically, phase A and B, by the end of phase B, you need to have proven to an independent review board that you know what you're doing and what your baseline design is will be good enough to meet your self-defined requirements. So that's basically at the end of phase B that you start phase C, you start to build, you start to cut metal. I was being asked around lunchtime, is there a phase where you know your mission is not going to get canceled? Unfortunately, there's no such thing, but it looks like once you are at the beginning of phase C, at least empirically, I don't know of any astrophysics missions that got canceled. It came close, but I don't know of any. So that's roughly when you really get serious about things, and it's also where you spend the most time. So if you look, for instance, I was looking at the numbers for Raman and Webb on the right, in terms of pre-phase A and the different phases, and there's no typical rule, but Raman, if we do, that's the asterisk here, is assuming that we launch on time. If we do launch in 2027, in May 2027, it will have taken about 16, 17 years of development from the recommendation from the decadal to launch. that's actually pretty good if you compare to Hubble and others. Webb obviously took more time. If you look at it, it's about 25 years, right, since 1996. And here, obviously, a very long phase D. So, I got a lot of colleagues who've been looking at how we might do better in the future, and it feels like Raman is already, if it keeps on track, we'll have, gotten back to less than 20 years of development from pre-phase A to launch. We hope to be able to do that with HWO as well. Key is really to do a lot of the technological development early on. It's been recognized by several of my colleagues, and Key is one of them here. So that's what we hope to do, like having maybe a bit of a longer pre-phase A, but once you start to have your marching army, really have a lot of the technologies already at hand and a very detailed plan of what you might want to do if one of them doesn't pan out. Easier said than done. And then, the cost for these missions, JW is about probably $11 billion, Raman is around 4, so that's orders of magnitude. And for HWO, we'll see. We'll probably be closer to Webb.
I'd like to hear as well, a lot of you have been asking, as a student or as a postdoc, how do I get involved with an instrument? How do I get involved with a mission? So I don't know, maybe Mike, would you like to speak to that for what students and postdocs have done in your group and what skills you found valuable and helped them to build?
Sure. I'll start by saying I remember the Sagan workshop 11 years ago. I looked it up, and I didn't have any pictures of me because I was sitting way in the back. I was doing radial velocity work at the time, and I said, wow, this is way better. Like, it's way more exciting. So I switched thesis topics after that. So that was, I guess, a short answer to your question about how I got involved in it. But as you've probably seen from a lot of these talks, it's a very rich and deep field that you can come at from many angles, a lot of technical depth, a lot of skills in observation, observing techniques. So there's many areas to approach it from. Getting involved in instrumentation, I think there's always a need for people who like to work on instruments, and so I think that's probably the least of the difficulties if you're at a center or doing an REU or looking for grad schools that do that kind of work. And as you get into the postdoc phase, there's maybe I won't comment so much on that, but there's also, as Bertrand and Dimitri know well, like huge numbers of people who are working on this at national labs and centers. So doing a postdoc in an academic institution isn't the only way to get involved. And having done that myself, it's not that different. It's quite interesting and fulfilling work, even with perhaps a little less freedom than you might have as a postdoctoral fellow. If anyone else wants to add.
Yeah, I often get this question for graduating students that wonder if a postdoc at a NASA center is as valuable as going or stay in the academia. I would say yes, definitely, and you have two examples here of we both did, right after grad school, we went to a NASA center and we worked there for a few years and then found our way back to academia. So that's definitely possible. So, and there's a lot of exciting work going on at all the NASA centers and Space Telescope. There are many of those around. There's IPAC here on campus. And this is fulfilling work. This is very important work, and you can stay there and do a fantastic career, or you can go back to academia. So really it's up to you.
Maybe I'll open it up to the floor also for some questions before I post more of my own.
So I don't know if this is a softball or not, but maybe for Bertrand, what do you think we learned most from CGI? Or will learn? Have we learned most, or will we learn it on orbit, or what?
we are launching it because we think we're going to learn more in
Wow.
orbit than we have in TVAC for sure. No, we've learned already quite a bit, I think, on things to do and not to do as we're building the instrument, and also a lot of lessons learned for INT. You know, INT is really difficult. You need to also build the instrument with INT in mind. There's a countless number of lessons learned. NASA doesn't. We don't like to call that lessons learned because it really means something specific. But you know, it goes from very mundane things about making sure you leave enough room with the cable so that you can actually access some of the things you need to align to maybe have your DMs ready early on and design your masks around them rather than the opposite. So there are things of that nature, very technical. But okay, the big picture is model validation. I mean, once we fly this thing and we observe with it, are the wavefront changes over time commensurate with what we expected them to be? I'm not too worried about sensitivities to aberrations because we've checked them and they're going to be what they are. But the level of wavefront instabilities that we're going to see, how does that compare to what we were predicting? That's something we're only going to be learning in orbit. Polarization effects also, they are pretty hard to model without having the full telescope, right? Because everything is coming from primary and secondary. So that we're also going to learn a lot about this. And a lot of us are observers. I think that there's only so much you can do with PowerPoint, right? In the end, you really need to have real data. The value of having real data with the type of instruments that we're going to want to be using for HWO for the next big science mission is invaluable. We've all seen that during our careers. I mean, we've developed like data reduction techniques that are really optimum because they were applied to real data. And before you have this data, you can't really think of how to deal with real life issues. So I don't know exactly all that we're going to learn, but I'm sure we'll learn a lot more still in space. Yeah.
Yeah, other questions in the room?
Hi, my name is Maria. I'm from the IFA, Hawaii. My question, I guess it's something three of you would have an experience with. Is there a key difference in between working on a space mission instrumentation versus an instrument project for a ground-based observatory? Differences or, I guess, similarities in work structure, environment, how the project itself is structured, and things like that?
Can try to answer that one. It's a good one. It's a good question. I would say on the ground you can make mistakes, more mistakes, because it's easier to go correct them than in space. So there's a little bit less pressure to have everything perfect or test everything. Although the standards are being raised for the next generation of ground-based telescopes, it's getting very close to NASA-like policies on quality control, but you're still allowed to make mistakes because the instrument, you can still access it and you can still fix it.
I'll just add one thing. I totally agree with everything that Bertrand and Dimitri said in the last question about the timelines for space missions, but there is a change happening where it's become a lot cheaper to launch things and you can launch a lot bigger things. And oftentimes in space missions, you can trade complexity for mass. And if we were to redo James Webb today, I'm not certain that it would be built primarily the primary, folding out and things like that, because you can fit Gemini telescope in a SpaceX Starship. So there's going to be, I think, changes happening where space missions will have a different risk profile than they do now, where we can tolerate some failure if we can launch 10 of them, for example. So there's that's starting to happen with some of the sort of intermediate $25 to $50 million class proposals from from NASA, but I expect it'll continue.
Have more questions in the room or online? Oh, let's hear from somebody we haven't heard from yet.
Hi, I'm Yinzi. I'm a grad student at Caltech. So I feel like all of you kind of have many hats, but two of them are as sort of like project managers, and then one of them is also like as a researcher yourself. I was wondering how you personally navigate situations where you see, like in allocating your time, things that I think you feel are the most beneficial to the field as a whole, and that like someone should do them, and if you don't do it, maybe it won't get done, versus things that you are like perhaps more interested in personally, when those things intersect and when those things don't intersect. How do you personally handle that?
Yeah, that's a really tough one. There's what you want to do and what you can do, always. So it's also, I mean, for me, it also changed over time, kind of naturally. I think at some point, you start to be more interested in how the decisions are being made. Once you've been on the other end of them, and you saw your mission canceled, for instance, which happened with TPFI or TPF at the time. I think that's when I really realized that science and engineering is very important, but is not the end of the story. And so that's when I started to get more interested in being part of the decision-making crew, and so once you start going that road, and as much as you like to also, play with your own data and submit science papers, it becomes really hard. Some people manage to do it. I would say it's after 9 p.m., but if that happens. But everybody has a different kind of mix of activities and priorities, but it is clearly something that I'm missing a little bit. I haven't really published like science results over the last 5 years, and I know it's going to be hard. So it's all a balance. But some project scientists, maybe have a lot of postdocs working with them, and they can at least take the pleasure to do a little bit of science once in a while. It really depends on the mission. I mean, for instance, the Roman Commonwealth is a tech demo, so it doesn't come with a lot of postdocs and scientists around it. And maybe the situation would be different for different science instruments. What do you think? Good answer.
Online questions? I want to make sure that we're addressing those if they've come in. No? Not yet? Okay. Yeah.
Yeah. So my question is, I'm returning from University of Arizona. Yeah. So my question is about like the Roman and JWST space telescope. It's really hard to design them to be upgradable, not like the ground-based telescope. Yeah, but we also know that NASA funding, we cannot anticipate that the U.S. House will cut down the budget again in the future. Yeah, so sometimes maybe if we can able to the project that could be upgradable, which means that we can make a mission be stage. So once we get more funding, we can upgrade those things. Is that possible for the space telescope to do that? Or another concept is probably we can have a telescope on the moon, so we can every time have a space test. We can transport from Earth to the moon and upgrade the telescope on the moon. Yeah.
So, I mean, I think was the question was sort of about in-space serviceability and are there any space telescopes that would consider multiple generations of instruments over the lifetime of the mission, or is that something considered maybe for a telescope on the moon or other platforms?
So HWO is supposed to be serviceable. So there's that now really in mind that. Yes. Yeah, sorry. So what I can tell you is that I think by Congress mandate now all of the next space telescopes need to be serviceable. So what that means exactly is not entirely clear. If you are interested in that topic, actually there's an upcoming workshop at Guarded, August 6th and 7th, so in 10 days from now, to deal about that topic in the particular context of HW. When we're talking about this type of investments, serviceable makes sense, right? If you want to keep the same telescope, like a Hubble has been serviced many times, we are not doing at all the same type of science as the Hubble was launched for, and that's thanks to a lot of new instruments that have been replaced up there. How we might do that at L2 is another question, but yeah, it's very much an important topic to maximize the return given the investments and allow new technologies to be infused in these telescopes 20 years from now.
Yeah, so I'm wondering about these, I'm asking a lot of PIs about this that do long-term projects, or at least people that are involved in long-term projects. How do you keep your team motivated? How do you make sure that you don't lose the momentum when the projects become really long?
Pay them well. No applause. Yeah, that's a tough one. I think it would be good if folks can also be involved in other projects, not just the one that takes so long, but if there are smaller projects with a faster return that they can work on at the same time, I think that's maybe that's a good option.
Yeah, it's almost like it's been my number one rule for many years. Like either keep a foot on the ground, where things generally are made a bit faster, except for ELTs now. It takes a long time. But yeah, you have to diversify your portfolio as much as possible. It could be ground and space. It could be 2 space projects, a very small one and a big one. But yeah, if you are on a big space project and it gets cancelled or dragged on forever, it's hard to keep people motivated, and it's really a big issue in terms of personal resources, right? Because we train these fantastic worldwide experts, and then there's some stop and go. Maybe people have personal lives and they don't want to take too much risks, and they see that their mission is on the verge of possibly being cancelled, so they leave. Then 2 years later, you tell them, "Oh, okay, we're back on." I'm like, "Well, sorry, moved on." So yeah, it's a big issue on these long projects, and I think one way to deal with that, when you are on that side of things, is to diversify your portfolio to some degree, not be 100% on the same project.
I would say also it's really critical to take pleasure in what you're doing on a day-to-day basis, setting small achievable goals for your research, so that you can celebrate small successes that advance the field as a whole. Because even if your big mission is cancelled, you've done something helpful, right? So you've developed a new technology, you've demonstrated some new application, maybe that will be taken off by some other mission later on, or some commercial applications, who knows? But setting small goals like that, I think is key to keeping the motivation up.
Agreed with everything said. Also, a lot of the things are connected. The sort of results you presented here for like digging dark holes on sky, that was originally developed in a lab that maybe no one really understood that it would be used on ground-based telescopes. You might also, if you've attended these talks, think that the biggest impediment in space would be speckles. And actually, at least in the infrared, detector noise would be 10 or 100 times higher. So maybe something less exciting is developing detectors that can do this, but these would be useful on the ground too. And you could do small projects on the side with that, and they benefit the whole community.